Hey y'all, now that we are done looking at triangles, it's time for us to add a couple more sides and look at polygons. And like triangles, we are going to begin our study of polygons by looking at the angles. We're going to specifically look at the sum of the interior angles of polygons. And we know from our polygon unit that the sum of the interior angles of a triangle is 180 degrees. Okay. Um, and so it would be super cool if we could use that information to help us figure out the sum of the angles of shapes with more sides. And we totally can do that if we do one very specific exercise, and that is to break the polygon up into triangles. And the most efficient way to do that is not, of course, to draw a whole bunch of little triangles in there. That's craziness. We want the vertices of the triangle to make up the interior angles of these polygons. And the way to do that is to pick one vertex of your polygon and connect that one vertex to all of the non-adjacent vertices of the polygon. So I'm not going to connect it to those two because those are just sides. I'm going to connect it to a non-adjacent vertex, which is way over here. And oh, surprise, surprise, what does that do? It breaks my quadrilateral up into two triangles, and the angles of these triangles are the vertices. If I add the angles up, they would be the quadrilaterals angles, which mean that the sum of the interior angles of this quadrilateral is going to be 360 degrees. Okay, so I started this little table here, number of sides, and I'm going to add like number of triangles, and I'm going to add another column that says interior angle sum. Okay, and we are going to use our inductive reasoning abilities to figure out the formula, which is going to happen here at n. So 3 sides is 1 triangle, or 180 degrees, right? 4 sides is 2 triangles, or 360 degrees. All right, so let's try the same thing with the pentagon. And this exercise of picking a vertex and connecting all of the non-adjacent vertices to figure out how many triangles that I can break my polygon up into might be familiar to you. When you study inductive reasoning, one of the questions that's very commonly asked is to do this and figure out how many triangles can be formed with this process. And the whole reason why you do that is later on you can prove this conjecture. So I have my pentagon, and it has 5 sides, and it can be broken up into 3 triangles, right? 3 little triangles here. And so it goes 3, and then 3 times 180 is 540 degrees. So the sum of the interior angles of any pentagon is going to be 540 degrees. And so now we're on to the end side. I have enough to figure out my pattern. So if I have an n-gon, and I repeat this process, and I pick a vertex, and I connect all the non-adjacent vertices from this vertex, right? Just kind of, it's an n-gon. I don't know how many sides it is. This is a generic polygon of n sides. We use the n-gon when we're looking at things like formulas, but I know if I went and connected all those vertices, that I would have n minus 2 triangles formed, and then the sum of the interior angles would be this number, which is n minus 2 times 180 degrees, which gives me the formula I need, and I'm going to write it a little bit bigger here. 180 degrees times n minus 2. This is the sum of the interior angles of a polygon with n sides. So of course this leads us to the conjectures, 2 of which are going to seem unnecessary, as you will soon see. So the first conjecture we get out of this is a quadrilateral sum conjecture, which basically says the sum of the measures of the interior angles of a quadrilateral is 360 degrees. And then C31 is a pentagon sum conjecture. Oh, the sum of the measures of the 5 angles of any pentagon is 540 degrees. Cool. But the important one is this one here, the generic one, the general one. C32, Polygon sum conjecture, says the sum of the n interior angles of an n-gon is 180 times n minus 2. So this is the one you really got to remember. And you can either memorize it or you can remember what it comes from, because C30 and C31 are covered in this, right? So I'm going to end this video with two questions that are interesting that you might want to explore. One is, do these conjectures apply to concave polygons? Because you'll notice all of the drawings I did were basically convex polygons. And the second one is, well, we use inductive reasoning to derive the formula, but how do we prove that formula for the polygon sums?